Welcome back. Today we will talk about thermal conductivity. Thermal conductivity refers to the ability of a given material to conduct, transfer heat. It is generally denoted by the symbol K, but can also be denoted by lambda and K. The reciprocal of its quantity is known as thermal resistivity. Materials with a high thermal conductivity are used in heat sinks, whereas materials with low values of are used as thermal insulators. Stable content. Thermal conductivity definitions. Thermal conductivity formula. Measurement of thermal conductivity. Effect of temperature on thermal conductivity. Factors affecting thermal conductivity. Frequently asked questions. What is thermal conductivity? Fourier law of thermal conduction, also known as the law of heat conduction, state that the rate at which heat is transferred through a material is proportional to the negative of the temperature gradients, and it's also proportional to the area through which the heat flows. The differential of this law can be expressed through the following equation, where Vt refers the temperature gradient, Q denotes the thermal flux or heat flux, and K refers to the thermal conductivity of the material in question. An installation describing the thermal conductivity of material in terms of the flow of heat through it provided above. In this example, temperature is greater than temperature 2. Therefore, the thermal conductivity can be obtained via the following equation: heat flux is equal to minus K, temperature 2 minus temperature 1 oblique thickness. Formula: every substance has its own capacity to conduct heat. The thermal conductivity of material is described by the following formula: K is equal to QL divided by A delta T, where K is the thermal conductivity in WMK. Q is the amount of heat transferred through the material in joules, second, or watts. L is the distance between the two isothermal planes. A is the area of the surface square meters. T is the difference in the temperature in Kelvin. Measurement. There exists several methods of measuring the thermal conductivities of material. These methods are broadly classified into two types of techniques: transient and steady state techniques. SI unit. Thermal conductivity is expressed in the term of following dimensions: temperature, length, mass, and time. The SI unit of quantity is watt per meter Kelvin, or Wm minus 1 minus K minus 1. It is generally expressed in the term of power, length, temperature. These units describe the rate of condition of heat through a material of unit thickness, and for each Kelvin of temperature differences. Steady states technique. These methods involve measurement where the temperature of the material in question does not change over a period of time. An advantage of these techniques is the analysis is relatively straightforward since the temperature is constant. An important disadvantage of steady state technique is that they generally require a very well engineered setup to perform the experiments. Examples of these techniques are Searle's bar method for measuring the thermal conductivity of good conductors, and least discount method. Transient techniques. In these methods, the measurement are taken during the heating up process. An important advantage of these methods is that the measurement can be taken relatively fast. One of the disadvantage of transient technique is the difficulty in mathematically analyzing the data from the measurement. Some example of these techniques include the transient plane source method, the transient line source method, and the laser flash method. Thus, there exist various methods of measuring the thermal conductivity of material, each with their own advantages and disadvantages. It is important to note that It is easier to experimentally study the thermal properties of solid when compared to fluids. Effects of temperature on thermal conductivity. Temperature affects the thermal conductivities of metal and non-metal differently. Metals, the heat conductivity of metals is attributed to the presence of free electrons. It is somewhat proportional to the product of the absolute temperature and the electrical conductivity as per the law, Franz law. With an increase in temperature, the electrical conductivity of the pure metal decreases. This implies that the thermal conductivity of the pure metal shows little variance with an increase in temperature. However, a sharp decrease is observed when temperature approaches 0 K. Alloys of metals do not show significant changes in electrical conductivity when the temperature is increased, implying that their heat conductivity is increased with the increase in temperature. The peak value of heat conductivity in many pure metals can be found at temperature ranging from 2 K to 10 K. Non-metals. The thermal conductivities of non-metals are primarily attributed to lattice, lattice vibration. The mean free path of the phenomenon does not uh, reduce significantly when the temperature are high, implying that the thermal conductivity of non-metal does not show significant change at a higher temperature. When the temperature is decreased to a point below at the by temperature or the heat conductivity of a non-metal decrease along with its heat capacity. Thank you very much.